Welcome to my presentation about the wonderful world of the VRP, also known as the frustration of computing pretty tours. My name is Maren and I'm a software engineer at Graphmasters. I work in the VRP service and we handle the logic behind our tour optimizations. And we can handle requests that come in either from customers or from different services. And we will look into first what happens when a request comes into our service at all, and then we will go down the ladder and see how we handle this. So when a request comes in, there are two ways and two services it can go to. And that is either the VRP service or the VRP tour service. We split this up into two services because we want to allow an always running system. And this is just the way we decided to do it. So on VRP Tour, there are all predictable incoming requests. That means either a driver tour update or just generally regularly scheduled data uploads. And on VRP, there are unpredictable requests that could take a long time or could max out our resources. And since we don't know what happens on VRP and how much computation we need on that service, we just split this up, and the drivers are always able to get their tours. So the request came in, we have either the VRP or VRP tour. The logic behind both tours is the same, it's just the split up on the services. And when we get this request in the end, we want to get a solution. We want to return a solution with an optimized tour for where all jobs are assigned and all the time windows are used and validated. And yes. So when it comes in, we start creating a data model. This data model is for just easier handling of the data, but it's also for us to pre-compute some values to make it easier to optimize later on, also to save some time later on. And this data model consists of kind of three big pieces, that be the vehicles, the drivers, and the jobs. And the vehicles, they have a general availability, they have an origin, they can have a trailer or no trailer, they can be allowed to reload. These are all data that comes into us and that influences the tour optimization. And for vehicles, we also have a transit and a distance matrix telling us, okay, how long will it take to go from this job and what is the distance? And this gets computed in a different service. And then we have the drivers that they could have a start time, end time, a latest start time, generally also a waiting strategy for jobs. So if they want to wait for a job time window or and to what time they want to wait, if there is like a cutoff at some point. And then we have the jobs, very similar, also having time windows then on them. And also you can set disallowed or restricted vehicles or drivers, generally saying, okay, this job is allowed on this vehicle, and this driver can't do this job because he hasn't got the right skill for it. And so this is generally what we have as a data model. What we also can do is for jobs to create groups, and we have 4 different kind of groups that we can put them in. They can be, for ones, they're called avoid splitting, then different vehicles, same vehicles, and also same vehicles but time dependent. And the thing is, some jobs, for example, they should arrive at the same time, and you want them to be on the same vehicle and just also at the same stop. So you say, okay, I don't want to split these jobs up against different vehicles. I want them all together. So you put them in a group, say this is avoid splitting, and then our system will take that in consideration. There's always a possibility that these groups will not be considered, but that is just always when there's a way better solution that can happen, or if you set it as it's not that important that you have to do it. There's also different vehicles. For example, chemicals and poison should not be on the same vehicle. The reason is pretty clear, I think. But there are also things that can be on the same vehicle. For example, our refrigerated food should be on one vehicle. But same vehicles, the difference to avoid splitting is that it doesn't matter if they are delivered at the same time, at the same stop. It just generally they have to be on the same vehicle. And there's like a very specific case that's called the same vehicle but time dependent, which means if, for example, there's a building that can be accessed after hours, but you need a key and only one driver has a key, that means that if you deliver these jobs in this time window, when there is after opening hours, you need a specific vehicle to access this building. So you can say, okay, if it's in this time frame, I want everything to be on the same vehicle so I can actually deliver them. Can get very complicated, but we do provide this. And I wanted to also explain that we have not just the group rules generally, but we also have a split up between strong and weak group rules. So for example, I have the same vehicle groups, and we say, okay, group A are just drinks, group B is food, and then you can say, okay, if this group rule is weak, that means I want all of the jobs in group A and all of the jobs in group B into one vehicle, but they don't have to be on one vehicle. But if you say, okay, this group rule is strong, it means that not just every job inside of a group, but also every groups that have this label same vehicle also have to be on one vehicle. So you get way more possibilities. And it makes it easier for us to compute if you already can say, I want everything on one vehicle. And then there's something a bit more complicated, say in different vehicles, where it's actually the opposite. So if you say, I have two different vehicle groups, group A with chemicals and group B with poison, then you say if this group rule is weak, then all of the chemicals can be on one vehicle and all of the poison can be on one vehicle, but group A and group B cannot be on one vehicle. You want them to be different. But if you say it's strong, then you're actually saying that not just these groups have to be on different vehicles, but also all of the jobs inside of these groups have to be on different vehicles, which just makes it very complicated, but it's there. So after we define this whole data model, we have the groups, we have our vehicles and drivers, we actually want to create a solution. And since it's an optimization, we always start just with a general initial solution. And these initial solutions, generally solutions have one specific pattern. And this means we have a vehicle, and then we just have an array which includes at first spot the driver, and then just all the jobs that come afterwards. And the jobs and the drivers just have an indice that we create in the data model, so we don't actually have to work with, let's say, an ID, which would make it just way more confusing. So this is a very simple way for us to see which job is on which vehicle with which driver and in what order. So to actually find a solution, we have to use some sort of search algorithms. And we have a few to pick from in our service as in search algorithms. And if you go through this topic, there is a way to either use heuristics or metaheuristics. And the difference between them is that a heuristic is generally problem dependent and just defines how to get a solution. So it can be appending just jobs to a vehicle, or it can be inserting a job to a vehicle. But they're generally greedy and can get trapped in a local minimum. And metaheuristics, on the other hand, are problem independent. And that means they can be used for a variety of problems. They kind of sit on top of a search and help guide it to increase the chance to find a global optimum. So the first one we actually use is the hill climb, which is kind of like a meta heuristic, but it's also a meta heuristic. It's very a bit fuzzy. Generally, it always tries to find a better solution. So it is kind of greedy, but it is like our standard thing, and then we apply other meta heuristics on top of this hill climb. So it's a very simple but actually effective way to find a good solution, and it just decides in the end, okay, what I have now must be the best solution, but of course it doesn't have to be. So we pair it generally with, for example, a guided local search, which normally if the hill climb finds a local minimum, then the actual function that defines, okay, how to get to this local minimum and how to calculate the fitness gets changed. So it's kind of like a penalty to get to this solution, and so it gets back to worse solutions, and just it tries to expand the search space. And this kind of approach is used in pretty much all of the meta heuristic that you also try to do, to not just accept good solutions but also worse solutions. This can be seen in the simulated annealing, which comes actually from annealing and metallurgy, which is a heat treatment for metal. And this means it involves heating and cooling, but not here metals, but a solution. And the heating means you accept a better solution, and the cooling means you accept a worse solution. So again, here you allow a more extensive search of the search space and just generally get more and hopefully in the end better solution. This takes a long time, but if you actually give it the time, it can provide very good results. A bit faster and a bit similar to the simulated annealing is the iterative search, which also accepts worse solutions, but has way less parameters than the simulated annealing, and so it is a bit easier to configure. But the results aren't as good as the simulated annealing, but they're still good results, so you can still use them. And then we also have the variable neighborhood search, which is a way that the actual search and what you do to create a new solution gets changed all the time. And for this, I have to explain what a neighborhood is. A neighborhood is just generally all solutions that form if you apply a specific move to a solution. So there are easy ones like you swap just 2 jobs or 3 jobs with other 3 jobs. You can move jobs from the beginning to the end, from the end to the middle, anywhere you want. And the solution that gets created with this one move, being a swap or a move lambda, where you just define how many you want to move, this describes the neighborhood. And we have actually 26 neighborhoods to choose from. So in this variable neighborhood search that I just talked about, we kind of mix it up which neighborhoods to use. And this provides, again, more possibilities to actually create solutions. And this is the key in generally optimization, to just get a variety of solutions and hope that you can find the best one. And we not just hope, you know at some point it can get better if the fitness doesn't change. But you can never know exactly if this is the optimum result or the optimum solution. You just have to trust that if you put in enough time and solutions, that it will be a good solution. So we have these kind of neighborhoods, and I wanted to show an example, which is also on the screen. It's a more difficult one. It's called 3-opt, and this means you have 3 sequences, and there's 7 possible ways how to combine these sequences. So you can see there are like case 1 till 7, and these are all different possibilities, and we have to calculate all of these possibilities. And we also have some moves that allow 26 cases, which was very difficult to program in the end, but they do give a good result. But also the very the very easy ones, like just moving something or swapping some jobs, is very practical and gives good results. So you don't always have to use the extra difficult and extra hard ones that take a long time. But you can use a variety of easy and complicated moves to create a variety of good solutions. So we talked about our solution. We talked about generally having what kind of search algorithms we have. So now we can actually create an initial solution. So in the end, after using all of this, let's say we use the hill climb with the guided local search, we now have a solution, and we now have to find out, okay, how good is this solution in the end? What is our fitness? And that's where the evaluator comes into play. And this evaluator is probably the biggest file in our service because it deals with all features and constraints that we as a service offer. For example, this can be just the evaluator does the actual traveling, calculating the time and the distance it takes. It involves breaks for the drivers, how long it takes to perform a job, service time. There can also always be, for example, a time to unhitch a trailer, and there's just a variety of possibilities how a tour in reality actually looks like. Sadly, it's not just, okay, a driver drives somewhere, lifts off a package, and then goes back. That's not how it works in reality. So we have to add a lot of features and a lot of constraints to make it as realistic as possible. So in the end, the evaluator is for calculating the fitness and dealing with all these features and constraints. and the fitness can be influenced by a variety of factors. I have here a spider diagram, kind of, that the users or the clients from Graphmasters can use on our career website. And this is a way for them to show us what weights we should apply to our fitness. So this shows us what is important to them. They have access to, for example, the vehicle and driver deployment, how much it should cost to actually use vehicles and drivers. So if you want to reduce your vehicles, you set this to very high. Then, of course, the distance and also the driver work time and the driver overtime. In logistics, it's pretty common to do overtime, so you can actually deliver all of the packages. So if you want to reduce this, you set this to very high, but also missed appointments, because jobs do have time windows and it is not very easy to consider them all. There are also some kind of secret factors that we do internally on our service. That's for one, the candy for distance and time, which sounds a bit weird, but generally it's just a factor that makes a tour more human and a bit more pretty, but not as good as an optimized tour would be like. Also skipping, which means skipping a job, because in the end you could also say, it's not as important if I don't do this job, it's way more important that the appointments get met, or that I use less drivers or less vehicles. So we also set this. And of course, actually considering the groups I talked about before. And for the time windows, I just want to shortly explain why it is kind of difficult to consider them, because we have a system. We have, say for a job time window, we have hard from and hard till, and they said, okay, before the hard from and after the hard till, this job is not possible. If you do the job in this time frame, this solution is not valid. And then we have the space between hard from and soft from, where we say, okay, it would be okay to do it in this time, but we would prefer to actually be between the soft from and soft till. So they get a penalty between the hard from and the soft from, or the soft till and the hard till, but it still would be a valid solution. But of course, if it's actually in the sweet spot between the soft from and the soft till, it's perfect, and we want it to be like this. So the job time windows are one of the most complicated things and the most biggest influences on tours. Yes, so we always have to consider this. Also, you can see that optimizations take way longer as soon as there are time windows on this, because it takes just a long time to find the solutions. So now we have created a data model from the incoming request. We have created an initial solution, and we evaluated this initial solution with the evaluator. And now we actually optimize the solution with these metaheuristics I just told you about, to also always evaluate it with the evaluator, see what fitness comes out, and at some point, either because we have a timeout or because we say there's some kind of stopping criteria, like if I haven't got any good new solutions for 5 iterations or for 5 seconds, I want to stop now. Then we get into the finalization, which just means there are some smaller neighborhoods, some easier neighborhoods, just moving around some jobs on vehicles, not actually between vehicles, but just on a vehicle to make the tour a bit more, just a bit even better. Yeah, it doesn't always have to give any results, but it's very practical to have like a last final step to just go over it once again and see what can I change and what can make it better. So now we have solutions. And now comes a very confusing part where we have to work with the drivers, because in the end, what I see on my screen if I work with this is just numbers. I don't even see how long it actually takes. I have everything in nanoseconds, so I don't know if if a tour takes 8 minutes, 8 hours, or 8 days, and I can't actually say. I just know, okay, if the fitness gets better, it's good, and if all of the constraints have been met, it's a good solution. But if you look at the tours on the website, or generally have a visualization of the tours and the jobs, you can see that there are very different kind of tours. and we do want to provide a way for the drivers to have an actual, like a very good tour that is something they would drive naturally to, so a very natural tour. So that means we have to define what actually is a good tour. So generally you would always say, okay, for example, left is a pretty round tour, it has no crossings, and the right one has one. So this could be like, we would just say the left one is a prettier one and the best one is a better one, and we want that. But you always have to keep in mind the way we visualize things are bird fly. So the routes between the jobs don't actually mean that the driver has to take this way. It could also mean that he has to do like some kind of curves, because that's how the streets are made. So you can't always define it by just how you look on top of it, but of course you can give like a general overview, okay, if you repeat a job or not. So I have another example. So you can see again, left is a crossing, but this doesn't have to be a bad thing. You can see from the streets that in the end he wouldn't actually drive a crossing. He would just drive around every single stop. But you can see on the right side there are a lot of crossings, and it doesn't look pretty, and the driver wouldn't actually want to drive this way, even if this is the optimized best solution, because he is the fastest possible, or is the fastest way possible. A driver would not want to drive this tour, because he says, okay, if I've already been to this stop, I don't want to drive back to do a similar stop. So we do have to put this into consideration if we create tours. And this is generally the logic part of our service and how this happens. Now I also want to talk about how our development process works and how we actually try to prevent bugs, because this is a live system we normally work on, just part of continuous development. So we always have to make sure that whatever we do is tested. So we do write tests for all of our new features, and we always have to compare results from our new, or with new features against old features. And if there are different results, as in the fitnesses from the same file and the same request are differently, or one takes a lot longer than the other, we do have to check that. And we also have to check if generally just the deployment works. And we also have pretty strict coding guidelines, so we generally like to go after the Go proverbs and after the effective Go guidelines. We also use very pedantic linters to have a very clean code base, and this is just generally how we try to make this all a bit cleaner and try to prevent from failing the system. Yes. And the next part is something a bit more technical I want to talk about, and that is our way of handling requests that come in, and we do get a lot of requests. So there are so many drivers out there now using NUNAV and sending us updates, and we actually have to use this, and we have to want to use all of our machines and all of our resources. So we have developed something that we call alchemy. If someone knows it or doesn't know it, it's actually a creature of the wizarding world of Harry Potter. And it can shrink and expand itself to depending on what room it is in. And it's kind of like a snake thingy, but it could fit into a little cup if that's all the space it got. But it also could fill up a whole auditorium. And this is what our idea behind the computing, behind our distributed computing. We want, if we don't have much space, we want it to shrink and still be able to handle a lot of requests. And if we have a lot of space and a lot of time, a lot of resources, we just wanted to fill everything up and use everything and max everything out. So this is how kind of alchemy works. So we have a request comes in. We had this in the beginning. It comes to VRP or VRP tour, and this alchemy server runs. And then the alchemy server creates a handler that handles this request. And this handler creates a master task. And this is a protected task that cannot be killed. So this is a task that runs the optimization of the request, or of the tour. And this master task recruits assistants. And these assistants also work on the same solution and just create way more solutions and do more searches. So we expand our repertoire of actually doing something. And these assistant tasks are kind of unprotected. There are sometimes some that are protected if we do need the computational power to calculate a request, but generally they are unprotected, so they can always be killed. So this allows us that if another request comes in, assistant tasks can be killed to make room for a new master task in their assistance, and this evens out in the end. And also, a monitor is overseeing then all of these solutions that come in and all of the costs in the master task. So all of the assistants just report back to the master and say, here, this is my solution, do with it whatever you want. And the master task looks into it and sees, okay, this is this fitness is better than the one I have or the ones I have stored. So this will be my new good solution. And then it returns that in the end. And again, here, either a timeout or a stopping criteria is set to stop at one point and say, okay, doesn't get better than this. And there are two ways to actually that the assistants handle this kind of tasks. And that can either be that all of the tasks work on the same solution, or they can work on different part of solutions. If they all work on the same solutions, it is way easier to actually record the solutions, but it also the chance to have just repeated solutions. If they all do the same, the chances are that they all find very similar solutions. And we don't actually would like that. This is actually the way we have to do it right now, or we are working on not doing it at some point, but right now this is how we do it because it is way easier to configure and to keep track of. But at some point we actually want that tasks work on different parts of the solution, so they actually, they just get a piece of a solution, optimize it, and then in the end we piece the solution back together. But this is kind of difficult, but this can result in better results. So we try to do this, but right now we haven't found a method that we are actually satisfied with, and this can reduce the quality of solutions if every task does the same, but we don't actually know if this approach of splitting up the solution is way better. We still have to test that. And this is generally what I want to talk about. I hope I could give you a good overview of our VRP service and that you learned something and got a bit entertained. Bye.